Okay, now that we have energy arriving into the atmosphere from the sun, we got to figure out what to do with that energy. And that is where temperature and heat come in. And that is what actually drives our atmospheric circulation. So let's take a look at that. What are some of the consequences of heat transfer? What the heck is heat? So let's just find some terms first. Temperature. Any molecule, atom, whatever, is moving. It has some kind of vibration or trying to go one direction or another. That motion is kinetic energy. And temperature is what is defined as kinetic energy. So the higher the temperature, the more the kinetic energy. The lower the temperature, the less the kinetic energy. If you look at the Kelvin temperature scale, where 0 degrees Kelvin is absolute zero, that says that technically at that point in time, molecules are not moving at all. Since we can't have negative kinetic energy, you can't have negative Kelvin. But that is a scale that actually represents kinetic energy. So the higher that number, water boils at 212 degrees Kelvin. So that would be the boiling point of water. And Celsius, we have 0 degrees is freezing, or 32 degrees Fahrenheit. Water boils at 100 degrees Celsius, or 212 degrees Fahrenheit. I'm sorry, I had the wrong reading for Kelvin there. And so with that, you can see the temperature constantly going up. There's other energies. Potential energy occurs in atoms and all that, and that's related to fusion and fission of atoms, atomic bombs. We could get into all that in a whole other course. Heat energy is just a transfer of energy. In other words, if you were to hold your hand close to a hot stove, your hand's going to get hot. Heat is coming from the stove into your hand. That is the transfer of kinetic energy from the stove to your hand. So heat is just a transfer of energy. Temperature represents kinetic energy. Heat is the transfer of that energy. So if you want to change the kinetic energy, you must have heat. So we know that temperature gradients exist. For example, we know the sun shines more over the equator and stronger there than it does at the North Pole. So immediately there's a temperature gradient. Well, the second law of thermodynamics says, hey, I hate temperature gradients. I'm going to do everything I can to get rid of the temperature gradient. So heat is going to flow in response to the gradient. It always flows towards lower temperatures, trying to eliminate the gradient. So the hotter the air is, heat is flowing from those hot areas towards colder areas. How can it get there? Well, we know we have radiation, conduction, convection, latent heat. So we're going to talk about those now. We've been talking about radiation for the last week with the sun's energy. So that is radiation. Electromagnetic radiation is radiation. So with the Earth, we know that we have ultraviolet radiation coming in and infrared radiation leaving. And we know that we have pretty close to a balance going on here because the Earth doesn't change temperature a whole lot. But what about if you have a cloudy day? Well, you have all that solar radiation reaching the clouds, but it's not getting all of it's not coming through. Some of it's being reflected and scattered. Then you have the Earth's radiation. It's going up into the clouds. We know water is a greenhouse gas. So some of that radiation is getting absorbed into the cloud and re-radiating back down to Earth. So interesting, when you're trying to figure out what the temperature is going to do in a cloudy sky, you have the greenhouse gas effect, and you have the fact that the all that sun's radiation can't get through. So overall, it winds up keeping it cooler, but because of the cloud cover, it's not as cool as it could get, especially at nighttime. So now we have other things called conduction. Did you ever see how hot the pavements get or walkways get? I remember going to Florida State, and one of the first things I learned was that everybody went barefoot down there. I thought, what? What is this? Everybody walked around campus barefoot, so I wanted to join in. Well, white concrete, no big deal in Florida. You can walk on it, not a problem. However, crossing a dark paved road is a whole different matter. That's where conduction takes place. That road absorbed the heat, didn't reflect it like those wonderful pavements did. So when you walked across the roads, you walked much faster because your heat was getting transferred into your foot, making it very hot. That's conduction. Convection is a process that occurs in the atmosphere and any other liquid. You ever watch water boil and you see these little bubbles come up in it? That's convection. It occurs in gases and any other liquid, so the fluid basically. And what it is, think about it, the earth heats the ground, the air below. That air begins to rise up, gets cooled by expansion. The higher it gets, sinks back down to the earth. So it's just a big circle of air. And it's occurring all the time. So that is one means that heat is being transferred from the earth into the atmosphere and vice versa, from the atmosphere back to the earth. Latent heating. The only element in the atmosphere that changes state is water. So water can go from a vapor to a liquid to a gas to a solid. So if it goes in that way, think about it. Vapor, the molecules are moving more, so there's a whole lot more energy there. Oh yeah, so if it goes into a liquid, some of that energy has to be released through condensation. So some heat is actually released into the atmosphere when water droplets form. Now, when it freezes, even more heat is released into the atmosphere. And it goes the other way. Oh yeah, ice, we'll say, becomes water. It melts. It had to absorb heat from the atmosphere. And finally, evaporation. When the water that's sitting on a puddle or whatever evaporates, it's absorbing heat from the sun so that it can evaporate back to water vapor. So now you have just added heat and taken away heat from the atmosphere depending on how water changed state. So that is why in a maritime climate, for example, if you live near an ocean, you wind up with temperature not changing as much. I love living near the ocean during the fall. Why? Because the ocean temperature is generally in the 60s here. That means that all that cold air you guys are getting in the Midwest, coming here to the coast, hitting the ocean, is being moderated tremendously by the ocean. When that happens, I don't get as cold. Works for me. Here is a wonderful heat balance we talked about in the atmosphere of all the different ways heat is being transferred. And there's also cumulus clouds are a great way of seeing heat lifted into the sky. You have the convection and you have a change of state. Oh yeah, you have condensation taking place because the water vapor went into water droplets. When that happened, heat was released. So that is a great way of moving heat from the ground into the air. We also know that there's a lot more solar radiation that arrives down around the equator than actually further north. And if you look at that, we must have a change of air masses somehow. atmosphere is always going to be trying to compensate for that. How's that do it? Well, one of the biggest movers, believe it or not, are tropical cyclones. The one that Lee, going on right now, for example, is pulling a tremendous amount of heat from the equator northward as it's moving. That is one of the ways it does it. Air mass exchanges. We can get very warm, humid air masses coming in out of the tropics, out of the Gulf of Mexico into the United States, for example, pulling up heat from there. Same thing with ocean currents. All these are ways we're trying to get heat to help warm the North Pole or the South Pole. Air masses, large volumes of air. We talked about it the very first week of class. They're another way of heat being transferred from one area to another. So these imbalances are what creates the weather. This imbalance is always going to be there. The Earth rotates. The Earth is at a tilt. We rotate around the sun, so we're getting a different amount of radiational heating. All of this, we have clouds, causes atmospheric weather circulations. One of the very first questions many of you got asked in your critical thinking was, why would a high temperature not occur till mid-afternoon? Well, here's the reasoning. First off, during the day, you have all that intense solar radiation coming in. Yes, there is some infrared radiation going out, but during the day, the solar radiation is stronger than the infrared radiation up until mid-afternoon. At that point, right there, we change, and the infrared radiation becomes stronger than the solar radiation. That is why the max temperature reaches there. Because if you have cold air masses and other things coming in, or clouds, they can adjust this solar radiation and the temperature gradient. But that's why your highest temperature occurs in the afternoon, because the amount of solar radiation is stronger than the infrared radiation till mid-afternoon. Also, interestingly, the infrared radiation is highest when the temperature is the warmest on the Earth. So late afternoon, infrared radiation from the Earth is highest. So once sun sets, we actually get faster temperature drop than we do later at night. Why is that? Because the infrared radiation was the highest at that time. Other things that impact the local temperature. I was at the beach last week for much of the week. Being right next to the ocean was definitely a little cooler than being inland. Also, sand reflects heat very much, so it kind of reflects it back into your face. So snow, very much. If you walk out in the middle of this after a snowstorm when bright sun shines out, you're going to see all kind of bright light, it seems like, out there. You really need to wear your sunglasses. All of that is a reflection of the solar radiation back into space. That is why it stays much colder when you have snow cover than if you don't. Finally, urban areas. They've been being studied for years. You can see, depending on the amount of houses and all, how the urban areas are hotter. DC was one example. Baltimore was another. I worked in Washington, D.C. area, so I know that National Airport had been the climate center there forever, for over 100 and some years. When National Airport, it was in that area, was built, there was not much in the way of buildings around it. It got fairly cool at night. Now, it's an urban area. It does not cool off nearly as much. So yes, temperatures are always going to be much warmer downtown D.C. than they are out at Dulles Airport, which is out in the country. The one final thing, I just wanted to give you an idea. Here's a stationary front across Virginia. Temperatures in the eastern part of Virginia are in the 70s and some 80s now already. Go west of that, back into Ohio, West Virginia, temperatures are in the 60s. Go further up, even some 40s back in here. So there's a nice temperature gradient here. Guess what? there actually is a transfer of energy, even though the air is advecting eastward, so it's pushing in colder air into Ohio. So cold air advection would bring in colder air. By the same token, over the ocean and stuff, we're pushing in warmer air back into my area. So we kind of got air masses meeting here, and that's why there's going to be thunderstorms later today. If you look aloft, you can see the same thing at 500 millibars with temperatures. And remember, we talked about heights, how the atmosphere expands when it's warm. Well, guess what? Some of the hottest temperatures right now are occurring in Texas, New Mexico, Arizona. Here's where high pressure is. Where's the colder air right now? Well, the colder air is up over Canada. And there's where lower pressure is. So all that description of why the atmosphere expands because the density is being reflected right here. And finally, I just wanted to show you a picture on a current image. Look at the temperature gradient here, much cooler, much tighter temperature gradient right along that frontal boundary. Then it slacks off after that. So hope you got something from all this, and let me know if you have any questions.